Hello, this is Richard Collins, your instructor in ATM101 Weather and Climate of Alaska here at the University of Alaska Fairbanks. Welcome to Unit 9. In this unit, we will be exploring wind, how it arises in the atmosphere, and the forces that govern it. How does wind have a particular speed and a particular direction? We will also be exploring latent heat of fusion in ice. As we melt ice, what is the energy required? This is an important issue in Alaska as we talk about springtime heating and the need to melt ice before we can heat the air in the ground during breakup. It also reminds us about water being unique, existing as a solid liquid gas in the atmosphere, and that those phase changes come with energy changes that are critical in questions of weather and climate. The reading for this week draws on Chapter 8 of Weather Studies, Wind and Weather, and draws on Chapter 5 of the Climate of Alaska, which is the pressure and winds in Alaska. The quick answer of how wind works in the atmosphere is as follows. The sun heats the earth differently in different regions. For example, warmer at the equator than at higher latitudes and coldest at the poles. Therefore, we get columns of air with different pressure variations in the warm regions than the cold regions, which create horizontal gradients of pressure aloft. The cold air sinks, the warm air rises, the pressure surfaces are higher in the warm columns than the cold columns. At a given altitude, there is pressure driving you from the warm region to the cold region. This is why we get airflow. This is the mechanistic reason of why we get the mechanism of why we get wind. The conceptual reason larger than that is the idea of energy transfer, that energy will always be transferred from where we have an excess of energy to where we have a deficit of energy. That's a general principle. It doesn't tell us how it happens, but now we begin to look, knowing our ideas from the ideal gas law, at how this actually happens and actually manifests itself as the wind patterns we see on Earth. The other key thing in winds is Coriolis forces, the idea that we are in a reference point where we are not at the center of the world. The world is rotating, we are on a world that's rotating, the air above us moves freely relative to the earth below, and therefore it's a classic question in physics and the natural world of rethinking your perspective to understand large-scale and global systems. It arises in astronomy, it arises in meteorology, and it arises in quantum physics, that we have to rethink our perspectives to get a deeper understanding of what's happening in nature. The other thing that I didn't mention, that I just want to mention quickly, is the issue of vertical pressure gradients in the atmosphere. Remember, in the vertical, the pressure is balanced by gravity, a very strong force. And so, in the first 5 kilometers of the atmosphere, the pressure changes by 500 millibars. The air does not rush upward from the high pressure of the ground to the lower pressure aloft because it's constrained by the force of gravity. The weight of the air doesn't allow this to happen in any serious way, except when we have updrafts associated with particular weather systems. But there's not a steady upward wind on the planet. If we had those kind of pressure gradients horizontally, it would make our most extreme hurricanes look like light and gentle breezes. There would be nothing on the surface of the earth that would be completely blown away. And so we have much smaller pressure gradients in the horizontal, giving us the significant wind systems that we see on the surface. In the lecture screencast for this week, I highlight what I think is important, but I also in this week go a little deeper than the textbook. I provide a variety of cartoons to show the physical processes at work, as well as picking some of the figures from the chapter in Weather Studies. It's important for you to be comfortable with these cartoons. These are the cartoons that will appear, schematic cartoons that you will have to identify the balance of forces on in the quiz and in the exam. So please take the time. You don't have to go back and read everything you know about Newtonian physics, but if you can work through how we're balancing forces, and think of forces as a shove. Think of somebody shoving you from one side and somebody shoving you from the other. Do you move? Do you stay still? What happens? But you don't necessarily have to go back to all your undergraduate physics books and or high school books and start rethinking everything you know about physics. I think you can work through this conceptually, and looking at the cartoons should help you. This week we're doing an indoor investigation, a benchtop investigation. There is no screencast. There is, however, concept questions. So you will have to fill out a worksheet and submit the answers to concept questions. So make sure you do every part of the unit and don't forget to do the concept questions and submit them in time. If you have any questions, don't hesitate to contact me or Cameron. Thank you and good luck.